far beyond the familiar stars of the night sky, beyond the glowing clouds where new suns are born, beyond the quiet worlds that circle distant stars, there exist objects so extreme that they seem almost impossible. They are the remnants of cosmic catastrophes, the surviving cores of giant stars that once blazed across the galaxy before ending their lives in explosions powerful enough to briefly outshine entire star systems. These remnants are known as neutron stars. If you could hold a piece of one in your hand, a fragment no larger than a grain of sand, it would weigh more than a mountain. Matter inside a neutron star is compressed beyond anything we can recreate on Earth. Atoms no longer exist there. The familiar structure of matter has been crushed away. Electrons and protons have merged together. What remains is an ocean of neutrons packed so tightly that the distinction between individual particles begins to blur. And yet, astonishingly, even this may not be the end, because nature appears to allow matter to be compressed even further. Somewhere beyond the limits of neutron stars lies another threshold, a final boundary, a point where even the most densely packed matter in the known universe may no longer be able to support itself against gravity. Tonight, we will follow a neutron star toward that boundary. We will watch as gravity slowly gains the upper hand. We will explore what happens when one of the densest objects in existence finally collapses. And we will ask a question that physicists still cannot answer with certainty. When a neutron star dies, does it simply become a black hole? Or could something stranger emerge from the collapse? Could there be another state of existence hidden beyond the event horizon, waiting in a region of reality that our current understanding cannot fully reach? The deeper we travel into this mystery, the more it begins to feel like a story, not only about stars, but about limits themselves. The limits of matter, the limits of knowledge, and perhaps the limits of reality. To understand why, we must first appreciate what a neutron star actually is. Imagine a star many times larger than our sun. For millions of years, it burns through its nuclear fuel, converting lighter elements into heavier ones deep within its core. Throughout its life, two immense forces struggle against one another. Gravity pulls inward, attempting to crush the star into a smaller and smaller volume. Meanwhile, energy released by nuclear fusion pushes outward, creating a delicate balance. This balance is what allows stars to exist. A star is not a static object. It is an ongoing negotiation between collapse and expansion, a constant cosmic argument between gravity and energy. But eventually, the fuel runs out. Fusion slows. The outward pressure weakens, and gravity begins to win. The result is one of the most violent events in the universe. The outer layers of the star explode outward in a supernova, while the core collapses inward at extraordinary speed. During this collapse, matter is squeezed so intensely that electrons and protons combine into neutrons. The core shrinks from millions of kilometers across to a sphere barely 20 kilometers wide. An entire star becomes a city-sized object. This is the birth of a neutron star. What emerges is unlike anything else in the cosmos. A single teaspoon of neutron star material would weigh billions of tons. Its magnetic field can be trillions of times stronger than Earth's. Its gravity is so intense that space itself becomes noticeably curved around it. Time passes more slowly near its surface. Light struggles to escape. The neutron star exists at the edge of what matter can endure. For decades, physicists believed this might represent the ultimate state of compression before the formation of a black hole. But nature has a habit of refusing simple answers. As researchers studied these extraordinary objects, they discovered that neutron stars may hide structures even stranger than their name suggests. The neutrons themselves are not fundamental particles. They are made of smaller components known as quarks. Under ordinary conditions, quarks remain confined inside protons and neutrons, never existing independently. Yet inside the crushing depths of a neutron star, the pressure becomes so extreme that some physicists suspect neutrons may begin to dissolve. Their identities may break apart. Their boundaries may disappear. The neutrons themselves may melt into an ocean of quark matter. If this happens, then a neutron star is not truly a neutron star all the way through. Instead, deep within its core may exist an entirely different form of matter, one that has never been directly observed anywhere in the universe, a hidden state buried beneath layers of unimaginable pressure. And this raises a fascinating possibility. Perhaps the collapse of a neutron star is not a simple transition from star to black hole. Perhaps there are intermediate stages, exotic states of matter, unknown structures, new forms of existence waiting between the familiar categories we have created. The universe often appears simple from a distance. Planets orbit stars, stars orbit galaxies, galaxies drift through space. But whenever we look closer, simplicity dissolves. Each layer reveals deeper mysteries beneath it. Every answer opens another question. And nowhere is this more true than in the study of extreme gravity. Because gravity is unique among the forces of nature. It never turns off. It never becomes repulsive. It never grows tired. Given enough time and enough mass, gravity always continues its work. Always pulling. Always compressing. Always seeking greater density. A neutron star survives only because quantum mechanics provides a final resistance against total collapse. The neutrons themselves obey rules that prevent them from occupying the same quantum states. This creates a pressure unlike anything we encounter in everyday life. Not a pressure produced by heat, not a pressure produced by motion, but a pressure arising from the fundamental architecture of reality itself. The universe appears to contain built-in rules that prevent matter from collapsing infinitely, at least for a while. The crucial question is whether those rules remain sufficient forever, or whether gravity eventually finds a way through. Imagine adding more mass to a neutron star. Perhaps it steals material from a nearby companion star. Perhaps two neutron stars collide and merge. Perhaps a chain of events slowly pushes it closer to its maximum possible mass. As the weight increases, the internal pressure must work harder and harder. The balance becomes increasingly fragile. The star enters a state of tension, a cosmic standoff between gravity and quantum mechanics. Neither side willing to yield, neither side capable of retreat, until eventually a critical point is reached, a moment unlike any other, a moment when the universe itself must decide what comes next. And it is here, at this threshold between survival and collapse, that our journey truly begins. Because the next step takes us toward one of the deepest mysteries in modern physics, the exact instant when a neutron star can no longer remain a neutron star, the moment gravity finally wins. And what happens afterward may be stranger than the black hole itself. There is a remarkable idea hidden within the universe, one that appears again and again across nature. Mountains can only grow so tall before their own weight causes them to collapse. Trees can only reach certain heights before gravity overcomes the ability of their trunks to support them. Even planets have limits. Add enough mass, and they transform into something entirely different. Nothing can grow forever. Everything has a threshold, and neutron stars are no exception. For all their incredible density and strength, neutron stars exist under a constant burden. Every second of their existence, gravity presses inward with unimaginable force. The star survives only because the strange quantum pressure inside its core pushes back. Yet this balance is not unlimited. There comes a point where adding just a little more mass changes everything. Physicists call this boundary the Tolman-Oppenheimer-Volkoff limit, often shortened to the TOV limit. It represents the maximum mass a neutron star can possess while still supporting itself against gravitational collapse. The exact value remains uncertain because it depends on the properties of matter under conditions we cannot fully recreate or observe. Current estimates place it somewhere around 2 to 3 times the mass of our Sun. That may sound enormous, but what makes it astonishing is the volume involved. Imagine compressing multiple suns into a sphere barely larger than a city. Not a city-sized cloud, not a city-sized plasma, a city-sized object, a solid gravitational monument made from the compressed remains of dead stars. And even that may not be enough, because once the TOV limit is crossed, something fundamental changes. The internal pressures that once resisted gravity begin to fail. Not instantly, not necessarily in a dramatic flash, but inevitably. The support structure of the star starts losing the battle. The neutron star enters a realm where every known mechanism of resistance becomes insufficient. Gravity continues inward. The matter continues compressing. The density continues rising, and the future becomes uncertain. What makes this moment fascinating is that modern physics cannot describe it with complete confidence. We know the beginning. We understand the neutron star. We know the probable ending. We understand black holes reasonably well from the outside. But the transition itself remains one of the most mysterious processes in nature. It is as if we possess the first chapter of a story and the last chapter of a story, while several crucial pages in the middle remain missing. The reason is simple. The physics governing these conditions pushes every theory we have toward its limits. General relativity describes gravity with extraordinary accuracy. It explains planets, stars, galaxies, gravitational waves, and black holes. Meanwhile, quantum mechanics describes the microscopic world with equally astonishing precision. Yet deep inside a collapsing neutron star, these two frameworks begin approaching one another in uncomfortable ways. Gravity becomes overwhelmingly strong. Matter becomes overwhelmingly dense. Space and quantum reality become inseparable, and our best theories stop fitting together neatly. This is one reason why neutron stars are so important. They are not merely exotic astronomical objects. They are laboratories, natural experiments running throughout the cosmos, places where the universe itself explores conditions far beyond anything humanity can construct. Every neutron star represents a question posed by nature. What happens when matter is pushed to its absolute limit? And every collapse may contain clues to answers we have not yet discovered. Imagine standing on the surface of a neutron star, if such a thing were somehow possible. The horizon would appear bizarre. Gravity would bend light around the star. The sky would distort. A single step could require enormous energy because the gravitational pull is hundreds of billions of times stronger than Earth's. Time itself would behave differently. A distant observer watching you from far away would see your clock running slightly slower than theirs. Not because your clock is malfunctioning, not because of an illusion, but because time genuinely flows differently in stronger gravitational fields. Already, before the star even collapses, reality is behaving in ways that challenge everyday intuition. And as the star becomes heavier, these effects intensify. Space curves more sharply. Time slows more dramatically. The distinction between ordinary matter and extreme matter becomes increasingly blurred. Eventually, the neutron star begins approaching a state where even light struggles to escape efficiently. This is not yet a black hole. The event horizon has not formed, but the object is drifting closer to a region where familiar concepts start losing meaning. A fascinating aspect of this process is how gradual it may appear from one perspective, and how violent it may appear from another. Inside the star, events unfold according to local physical processes. Matter compresses, densities rise, pressures change, particle interactions become increasingly exotic. But to a distant observer, the effects of relativity create a strange visual story. As gravity strengthens, time near the collapsing object slows relative to the outside universe. The deeper the collapse progresses, the more extreme this effect becomes. The star appears to move toward a frozen state, toward stillness, toward a kind of gravitational silence. This duality appears repeatedly throughout modern physics. Reality depends on perspective. Neither observer is wrong. Each witnesses a different aspect of the same event. And this idea carries philosophical implications far beyond astrophysics. We often imagine the universe as containing one absolute narrative, one definitive version of events. Yet relativity teaches something subtler. Different observers can experience different realities, while all remaining correct within their own frames of reference. Time itself becomes flexible. Distance becomes relative. The cosmos reveals itself not as a rigid stage, but as a dynamic relationship between observers and events. Neutron star collapse pushes these lessons to extraordinary extremes. the closer we approach the threshold of black hole formation, the stranger our assumptions become. Questions emerge that sound almost philosophical. Where exactly does a black hole begin? At what precise moment does the event horizon appear? Can there be transitional states that exist only briefly before complete collapse? Could entirely new forms of matter arise during the final stages? For decades, physicists have explored possibilities with names that sound almost mythical: quark stars, strange stars, hybrid stars, objects composed not primarily of neutrons, but of more fundamental particles liberated by immense pressure. Some models suggest that before a neutron star becomes a black hole, it might pass through these intermediate phases. The core could undergo dramatic transformations. Neutrons might dissolve into quark matter. Quark matter might reorganize into even more stable configurations. The star could temporarily become something we have never directly observed, a cosmic species existing only in the universe's most extreme environments. Whether these objects truly exist remains uncertain, yet the possibility itself is revealing. It reminds us that nature often possesses more imagination than our expectations. Again and again, scientific history teaches the same lesson. Reality is rarely simpler than we assume. Most often, it is stranger. Centuries ago, stars seemed like eternal points of light. Then we discovered they are giant nuclear furnaces. Atoms once appeared indivisible. Then we found protons, neutrons, and electrons. Those particles seemed fundamental. Then we discovered quarks. Every layer opens another. Every certainty becomes a doorway. And now we stand before one of the deepest doorways of all, the threshold where matter may cease being matter in any recognizable sense, the threshold where gravity may dominate completely, the threshold where the distinction between object and spacetime begins to dissolve. Because this is the extraordinary thing about black holes. Unlike planets or stars, they are not merely objects existing within space. In a profound sense, they become part of the geometry of space itself. The collapse of a neutron star is not simply matter becoming denser. It is matter reshaping reality, bending spacetime so severely that entirely new structures emerge, structures that challenge our understanding of causality, information, and existence itself. Yet before we reach the black hole, there remains an important possibility to explore. What if collapse does not happen immediately? What if there exists another stage hidden between neutron stars and black holes, a state where matter enters a form more exotic than anything currently known? State where the star survives, at least temporarily, by becoming something fundamentally new. The deeper we travel into the heart of a neutron star, the more a surprising realization begins to emerge. A neutron star is not truly made of neutrons in the way a beach is made of sand, or a cloud is made of water droplets. The word neutron is ultimately just a label, a useful description for a certain arrangement of matter under certain conditions. But nature rarely respects the categories we create. When the environment changes enough, the categories themselves can dissolve. And inside a neutron star, the environment becomes so extreme that even neutrons may lose their identity. To understand why, imagine descending toward the center of one of these remarkable objects. Near the surface, conditions are already unlike anything found on Earth. Atomic nuclei are packed together into strange crystalline structures. Matter behaves in ways that would seem impossible in any ordinary laboratory. Some physicists have even described parts of the neutron star crust as forms of nuclear pasta. The name sounds playful, but the underlying reality is astonishing. At certain densities, matter appears to organize itself into shapes resembling sheets, tubes, and tangled structures. These formations emerge because competing forces are trying to arrange matter in the most stable configuration possible. Even before reaching the core, the universe is already inventing structures that sound more like abstract art than physics. Yet this is only the beginning. As we move deeper, pressure rises continuously. The weight of the entire star presses downward, layer upon layer, kilometer upon kilometer, billions of tons pushing on billions of tons. Eventually, we enter a region where individual atomic nuclei can no longer maintain their separate identities. Matter becomes a nearly continuous sea of neutrons. This is the environment that gives neutron stars their name. But what happens if the pressure continues increasing? What happens if gravity keeps squeezing? What happens when even neutrons are no longer capable of maintaining their structure? This question takes us into one of the most speculative and fascinating areas of modern astrophysics, because neutrons themselves are not fundamental. They are built from smaller particles known as quarks. Specifically, neutrons contain three quarks bound together by the strong nuclear force, one of the most powerful forces in nature. Under normal circumstances, quarks are never found alone. No matter how hard physicists try, pulling quarks apart simply creates new particles rather than isolated quarks. Nature appears determined to keep them confined. Yet neutron stars may push matter into conditions where this confinement begins to break down. Imagine the pressure becoming so overwhelming that individual neutrons can no longer remain intact. Their boundaries blur. Their internal structures overlap. The distinction between one neutron and another starts disappearing. Instead of separate particles packed tightly together, matter may transform into an ocean of liberated quarks. Not billions of individual neutrons, not trillions of separate particles, but a continuous sea of quark matter extending through the core. If this state exists, it would represent an entirely different phase of matter. Not a solid, not a liquid, not a gas, not even a neutron fluid. Something fundamentally alien compared to anything humans encounter in everyday life. A form of matter created only under conditions so extreme that nature rarely permits its existence. The strange thing is that this possibility is not merely science fiction. There are serious physical reasons to suspect it may be real. Particle accelerators on Earth have briefly produced environments where quarks appear to move freely within what is known as a quark-gluon plasma. For tiny fractions of a second, matter enters a state resembling conditions that existed shortly after the Big Bang, before atoms, before stars, before galaxies, before almost everything we recognize. The universe itself may have once existed as an ocean of freely moving quarks. If so, then the core of a collapsing neutron star may not merely be evolving towards something new. It may be returning to something ancient, something that existed at the dawn of cosmic history. There is a poetic symmetry hidden within that idea. The deeper gravity compresses matter, the further backward in cosmic history it seems to travel. Layers of complexity are stripped away. Atoms disappear. Nuclei disappear. Neutrons disappear. And beneath them all, more fundamental structures emerge. It is almost as though gravity acts like an archaeologist, excavating deeper and deeper layers of reality, removing the familiar, exposing the primitive foundations beneath. But the mystery grows even stranger. Some physicists have proposed that quark matter might not merely exist as a temporary phase. It may actually be more stable than ordinary matter under certain conditions. This leads to one of the most fascinating hypotheses in modern astrophysics, the possibility of strange matter. To understand this idea, we must introduce another type of quark. Most everyday matter is built from up quarks and down quarks. These form protons and neutrons. Yet nature contains additional varieties of quarks as well. One of them is called the strange quark. Under ordinary conditions, strange quarks are unstable and disappear quickly. But inside a neutron star, ordinary conditions no longer apply. The immense pressure may allow strange quarks to persist. And if enough strange quarks accumulate, matter itself may enter a completely new state, a state known as strange matter. If strange matter is more stable than ordinary nuclear matter, an extraordinary possibility emerges. Entire stars could exist that are not neutron stars at all. They would look similar from the outside. Their masses might be comparable. Their sizes might be comparable. Yet internally they would be profoundly different. Instead of being composed primarily of neutrons, they would be made from vast oceans of strange quark matter. These hypothetical objects are known as strange stars. And if they exist, they may represent a hidden population of cosmic objects scattered throughout the universe. Stars that appear familiar while secretly containing one of the most exotic forms of matter imaginable. The idea sounds almost fantastical. Yet modern observations have not ruled it out. In fact, some measurements of particularly massive neutron stars have led researchers to wonder whether at least a few observed objects might belong to this category. The evidence remains uncertain. The debate continues, but the possibility itself changes how we think about stellar collapse. Because if strange stars exist, then the journey from neutron star to black hole may not be a single step. There may be multiple stages, multiple identities, multiple forms of existence waiting along the way. A neutron star might first become a hybrid star, then perhaps a quark star, then perhaps a strange star, and only afterward continue toward black hole formation. Reality may contain a ladder of increasingly exotic states hidden beneath ordinary matter. The deeper gravity pushes, the stranger the universe becomes. What makes this idea so captivating is that it challenges one of our most basic assumptions. We often imagine matter as something fixed, a stable substance that simply gets compressed or expanded. But modern physics suggests something very different. Matter is not a thing, it is a pattern, a temporary arrangement of deeper ingredients. Under sufficient pressure, those arrangements change. Under sufficient energy, they transform. Identity itself becomes fluid. The atoms in your body are one arrangement. A neutron star is another. A quark star may be another still. The distinction lies not in what reality is made from, but in how those ingredients are organized. And perhaps the same lesson extends beyond physics. Perhaps many things we consider permanent are merely temporary structures, patterns that emerge, persist for a time, and eventually transform into something new. Stars evolve. Galaxies evolve. Even the universe evolves. Nothing remains fixed forever. Everything participates in an ongoing process of transformation. Neutron stars simply reveal this truth at the most extreme scales imaginable. Yet even strange stars and quark stars may not represent the final stage, because gravity never stops asking its question. How much further can matter be compressed? How much deeper does reality go? And eventually, regardless of what exotic states may exist along the way, collapse may continue. The star may cross a boundary from which no known force can save it, a boundary where matter ceases to be the central story, a boundary where space-time itself becomes the protagonist. And as we approach that threshold, another mystery begins to emerge. A mystery not about matter, but about horizons, about information, about the exact moment the universe hides a region of reality from everything outside it. There is a moment during the collapse of a massive star that may be one of the strangest events in the entire universe. No explosion announces it. No flash of light marks its arrival. No cosmic alarm sounds across the galaxy. And yet, from that moment forward, reality is permanently changed. A boundary appears. A boundary unlike any other known in nature. Not a wall made of matter. Not a surface you could touch. Not a physical object in the conventional sense. Instead, it is a limit built into the structure of space-time itself. Cross it, and every possible future points inward. Cross it, and escape becomes impossible. Cross it, and even light, the fastest thing in the known universe, can no longer return. This boundary is called the event horizon, and the formation of an event horizon is what transforms a collapsing star into a black hole. At first glance, the idea sounds simple. Gravity becomes strong enough that nothing can escape. But the deeper physicists have studied black holes, the stranger this concept has become. Because an event horizon is not merely a region where gravity is powerful. There are places in the universe where gravity is immense without forming black holes. Neutron stars themselves possess gravitational fields so strong that they dramatically bend light and slow time. Yet they are not black holes. The difference lies in something more profound. A neutron star still possesses possible paths leading outward. A photon emitted from its surface can, in principle, escape into space. The journey may be difficult, the climb may be steep, but escape remains possible. Inside an event horizon, this changes completely. The geometry of space-time itself becomes distorted in such a way that every possible path leads inward. This is difficult to visualize because human intuition evolved in a world of weak gravity. We instinctively imagine space as a fixed stage on which objects move. General relativity tells a different story. Space and time are not passive backgrounds. They are dynamic participants in reality. They bend, they stretch, they curve. And near a black hole, they curve so severely that the distinction between movement through space and movement through time begins to blur. Outside a black hole, traveling into the future is unavoidable. No matter what you do, tomorrow arrives. Next year arrives. Time carries you forward. Inside an event horizon, moving toward the center becomes just as unavoidable. The singularity lies in the future in much the same way tomorrow lies in your future now. You do not choose to move toward it. Reality carries you there. The event horizon is therefore not merely a prison. It is a transformation in the structure of causality itself. This is one reason black holes continue to fascinate physicists decades after their discovery. They are not simply dense objects. They are regions where our ordinary understanding of reality begins to fail. And yet, the actual birth of an event horizon remains surprisingly mysterious. Imagine a neutron star that has accumulated too much mass. Perhaps it merged with another neutron star. Perhaps it slowly consumed matter from a nearby companion. Perhaps exotic processes within its core altered its stability. Whatever the cause, the result is the same. The internal pressure is no longer sufficient. Gravity gains the advantage. Collapse begins. At first, the star shrinks. Its radius decreases. Its density increases. The pressure rises dramatically. The interior becomes hotter, more chaotic, more extreme. Every second brings greater compression. And then something remarkable happens. The star eventually contracts within a critical radius, known as the Schwarzschild radius. This radius depends on the object's mass. For an object the mass of our Sun, it is only about 3 kilometers. For larger masses, the radius increases proportionally. Cross this boundary, and an event horizon forms. The object becomes a black hole. But here, a fascinating question emerges. What exactly happens at that moment? Does the horizon suddenly appear? Does it grow gradually? Is there a precise instant when the universe changes state? Modern physics provides mathematical descriptions, yet the intuitive picture remains surprisingly elusive. Part of the difficulty arises because different observers experience the collapse differently. Imagine watching from a safe distance. You observe the neutron star shrinking under its own gravity. As it approaches the critical radius, time dilation becomes increasingly extreme. Clocks near the star appear to run slower and slower. Light escaping from the surface becomes increasingly redshifted. The star appears dimmer, redder, more sluggish. Eventually, it seems to freeze near the horizon. Its final moments stretch indefinitely. To the distant observer, the collapse never appears fully complete. The star simply fades, slows, disappears from view. Yet now imagine riding alongside the collapsing matter. Your experience is entirely different. Time feels normal. The collapse proceeds. The horizon forms, and you cross it without encountering any visible barrier. No wall, no flash, no obvious signal announcing that the crossing has occurred. You simply continue inward. This contrast is one of the most astonishing features of black holes. Two observers witness radically different versions of the same event. Neither observer is mistaken. Both descriptions are correct within their respective frames of reference. Reality accommodates both perspectives simultaneously. The universe appears comfortable with a level of complexity that often exceeds our intuition. And perhaps this should not surprise us. After all, why should the deepest structures of existence conform to instincts shaped by life on a small planet? The cosmos was under no obligation to make itself intuitive. It merely had to be consistent. Black holes reveal that consistency does not always resemble common sense. As collapse continues, another mystery begins to emerge. What exactly is happening to the matter itself? When the neutron star first formed, matter remained recognizable. Atoms vanished, nuclei merged, neutrons dominated. Perhaps quark matter appeared. perhaps strange matter emerged. But once the event horizon forms, the story changes. The matter that created the black hole becomes hidden from outside observation. An external observer can measure only a few properties: mass, charge, angular momentum. Everything else appears to vanish behind the horizon. This astonishing simplification led physicist John Wheeler to popularize the phrase, "black holes have no hair." The idea was that black holes erase complexity. A black hole formed from collapsing stars appears remarkably similar to a black hole formed through entirely different processes. From the outside, much of the detailed history seems lost, and this creates one of the deepest puzzles in theoretical physics. Can information truly disappear? Suppose a neutron star collapses into a black hole. Every particle within it carried information. Every quantum state, every interaction, every configuration of matter. Where does all that information go? Does it remain hidden inside? Does it somehow survive on the horizon itself? Can it be destroyed? For decades, physicists have wrestled with these questions. The answers remain incomplete. In fact, the information paradox remains one of the central unsolved problems in modern science. And strangely enough, it hints that black holes may not represent the end of understanding. Instead, they may point toward a deeper theory, still waiting to be discovered, a theory that unifies gravity and quantum mechanics, a theory capable of describing what truly happens inside the most extreme objects in the universe. Because the closer we examine black holes, the more they resemble crossroads, places where multiple branches of physics converge: general relativity, quantum theory, thermodynamics, information theory, all meeting at a single point. And whenever different branches of knowledge collide, history suggests that something profound is waiting beneath the surface. The event horizon may therefore be more than a boundary in space. It may be a boundary in understanding, a place where our current maps of reality begin to fade, a place where familiar concepts stop working, a place where the next great scientific revolution may eventually begin. Yet even now, another question lingers, a question that grows increasingly difficult to ignore. If the event horizon forms and the collapse continues, what ultimately happens at the center? Does matter compress forever? Does a singularity truly exist? Or does nature possess one final layer of structure hidden beneath everything we currently know? If a neutron star collapses beyond every known limit, if gravity overcomes every form of pressure that matter can provide, if an event horizon forms and the inward fall continues, then according to the equations of general relativity, there is only one destination remaining: a singularity. The word itself carries an unusual feeling. It sounds less like a physical object and more like a warning, a place where something has gone wrong, a place where the map ends, a place where the mathematics continues, but understanding does not. For decades, singularities have occupied a strange position within physics. They emerge naturally from Einstein's equations. The mathematics predicts them with remarkable consistency. Yet many physicists suspect that singularities are not real objects in the conventional sense. Instead, they may represent the limits of the theory itself. To understand why, imagine studying the ocean with a map that describes every wave, every current, and every coastline. The map works beautifully across thousands of kilometers. It predicts tides, it explains storms, it allows ships to navigate safely. But then, at one particular location, the map suddenly labels an area with a single sentence: infinity. Not an island, not a reef, not a whirlpool, just infinity. At that point, you would probably suspect that the map has reached its limits. The problem may not be the ocean. The problem may be the description. This is how many physicists view singularities. When the equations predict infinite density, infinite curvature, and infinitely strong gravitational fields, it may not mean nature truly contains infinities. It may mean our current mathematical framework is incomplete. And if that is true, then the center of a black hole becomes something even more fascinating. Not the end of knowledge, but the beginning of a deeper layer of reality. According to classical general relativity, once matter passes the event horizon, collapse continues relentlessly. The neutron star's remaining structure disappears. The matter continues inward. Distances shrink. Density rises. Space-time curvature increases. Everything is compressed toward an increasingly tiny region. Eventually, the equations describe all the mass becoming concentrated into a point with zero volume, a point where density becomes infinite, a point where space-time curvature becomes infinite, a point where the known laws of physics cease functioning. This is the singularity. Yet, there is something deeply unsettling about infinities in science. Again and again throughout history, infinities have often signaled that a theory requires revision. When physicists first calculated the energy of electrons using certain early models, infinities appeared. The solution was not that electrons possessed infinite energy. The solution was better physics. When classical theories predicted ultraviolet catastrophes in radiation, infinities emerged. The solution was quantum mechanics. Nature repeatedly teaches the same lesson. Infinity is often the universe's way of telling us that our understanding has reached a boundary. And nowhere is that lesson more relevant than inside black holes, because the singularity is where two of humanity's greatest theories collide. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes reality as a world of probabilities, fields, and discrete interactions. Both theories work extraordinarily well. Both have been tested repeatedly. Both have survived every challenge we have thrown at them. Yet they do not fit together cleanly. Inside a black hole, both become essential. Gravity is overwhelmingly strong. Quantum effects become overwhelmingly important. Neither theory can be ignored, and yet we lack a complete framework that unites them. This missing theory is often called quantum gravity. Physicists have spent decades searching for it. String theory, loop quantum gravity, causal dynamical triangulations, quantum geometry. Various approaches attempt to describe what happens when spacetime itself becomes subject to quantum rules. And remarkably, many of these theories suggest that singularities may disappear, not because black holes vanish, not because gravity weakens, but because spacetime itself possesses deeper structure than Einstein realized. Consider a simple analogy. From far away, a beach appears smooth. As you walk closer, you notice individual grains of sand. The apparent smoothness was an illusion, created by scale. Many physicists suspect something similar may apply to spacetime. Perhaps space is not infinitely divisible. Perhaps there exists a smallest possible scale, a fundamental graininess hidden beneath the smooth fabric described by relativity. If so, then infinite compression may become impossible. The collapse could reach some ultimate quantum limit, not a singularity, not infinity, but something entirely different, something finite, something physical, something real. This possibility has profound implications, because if singularities are replaced by quantum structures, then the interior of a black hole may not be a featureless point at all. It may contain hidden complexity, hidden geometry, hidden states of matter, entire regions governed by laws we have yet to understand. In some models, collapse eventually encounters quantum pressure that halts further compression. In others, spacetime undergoes a transition into a new state. In still others, the singularity is replaced by an exotic quantum core. The details vary dramatically, but a common theme emerges. The classical singularity may not be the final answer, and if it is not, then an extraordinary question appears. What exactly lies beyond the collapse? Because remember how this journey began, with a neutron star, a physical object, a remnant of a dead star, a sphere of matter balanced precariously against gravity. Then collapse began. Neutrons may have dissolved. Quark matter may have emerged. The event horizon formed. The black hole was born. And now even the singularity itself is being questioned. Each stage removes another layer of familiarity. Each stage reveals a deeper mystery. It is almost as though gravity acts not merely as a force, but as a probe, a mechanism that peels away successive layers of reality. Atoms are removed. Particles are removed. Space-time itself may eventually lose its familiar form. The deeper the collapse proceeds, the further we move from ordinary experience. And perhaps that is why black holes, exert such a powerful fascination on the human imagination? They are not merely astronomical objects. They are symbols of the unknown. Every civilization has had horizons, edges beyond which understanding fades. Ancient oceans, unmapped continents, invisible worlds beneath the atom. Black holes represent the modern version of that frontier, a place where certainty gives way to mystery, a place where our best theories begin to whisper rather than speak. And yet, despite all the uncertainty, one thing appears increasingly clear. The universe does not seem eager to provide simple endings. Again and again, what appeared to be a final answer became the doorway to a deeper question. Atoms were not fundamental. Neither were protons. Neither were neutrons. Even spacetime itself may not be fundamental. Every layer hides another. Every conclusion reveals a new beginning. This raises a possibility that would have sounded absurd only a century ago. What if a black hole is not the final state of collapse? What if the object formed after a neutron star's death is itself only an intermediate stage? What if there are structures beyond black holes, hidden beneath the limits of our current theories? The idea sounds almost impossible. After all, black holes already represent some of the most extreme entities known to science. Yet history encourages caution whenever we are tempted to declare something final. The universe has repeatedly demonstrated that our imagination tends to underestimate its complexity. And so the question returns. The same question that has quietly followed us since the beginning of this journey. When a neutron star finally collapses, does it simply become a black hole? Or is the black hole itself another step towards something deeper? There is a curious pattern that appears throughout the history of science. Whenever humanity discovers a new frontier, the first explanation is rarely the final one. Ancient astronomers believed the stars were fixed lights attached to a celestial sphere. Later generations learned that the stars were distant suns. Then those suns became nuclear furnaces. Then those furnaces became laboratories of quantum physics. Every time a mystery seemed solved, the solution revealed a deeper mystery waiting beneath it. Black holes may be no different. Today, black holes occupy a unique position in our understanding of the universe. They are among the most successful predictions of general relativity. We have observed their influence on nearby stars. We have detected the gravitational waves produced when they collide. We have even captured images of the glowing material surrounding their event horizons. And yet, despite these achievements, many physicists suspect that our current picture remains incomplete. Not necessarily wrong, but incomplete. Because if singularities are not real, and if quantum gravity ultimately modifies what happens during collapse, then the object we call a black hole may conceal a far richer internal reality than the classical equations suggest. This possibility has inspired some of the most imaginative ideas in theoretical physics. Ideas that sound almost like science fiction, yet arise directly from serious attempts to reconcile gravity with quantum mechanics. One such idea is the gravastar. The name is short for gravitational vacuum star. At first glance, a gravastar resembles a black hole. From a distance, it may possess nearly the same mass, nearly the same size, and nearly the same gravitational influence. But internally, it is profoundly different. Instead of containing a singularity, the collapsing matter triggers a phase transition in spacetime itself. The interior becomes a region of exotic vacuum energy, surrounded by an incredibly thin shell of matter. In this picture, collapse never reaches infinite density. The star transforms before the singularity can form. Gravity pushes inward. Vacuum energy pushes outward. A new equilibrium emerges. The result is an object that mimics many properties of a black hole, while avoiding some of the conceptual difficulties associated with singularities. Whether gravastars actually exist remains uncertain. No observation has confirmed them, yet their significance lies not merely in their existence. Their significance lies in what they represent. They demonstrate that alternative outcomes are possible. Nature may have more options available than our simplest models suggest. Another proposal is even stranger: the black star. Unlike a classical black hole, a black star never fully completes its collapse. Instead, the formation of the event horizon is delayed by quantum effects. To distant observers, the object appears almost identical to a black hole. It becomes extraordinarily compact. Its gravity becomes extreme. Its light becomes heavily redshifted. Yet a true horizon never fully forms. The collapse continues more and more slowly, approaching completion without ever quite reaching it. The object becomes a kind of frozen remnant, suspended near the threshold of black hole formation, a star trapped forever on the edge of becoming something else. There is something deeply intriguing about this idea. It transforms the event horizon from an absolute boundary into an asymptotic destination, a goal approached indefinitely but never entirely achieved. And if such objects exist, they remind us once again that reality may be subtler than our categories. The universe rarely seems interested in neat definitions. It prefers gradients, transitions, intermediate states, regions where certainty dissolves into possibility. Perhaps nowhere is this more apparent than in the search for quantum gravity itself. Many modern theories suggest that spacetime is not continuous. Instead, it may possess an underlying microscopic structure, tiny units, fundamental building blocks, a hidden architecture beneath the smooth geometry described by Einstein. If this is true, then collapse may eventually encounter a new form of resistance. Not resistance from matter, not resistance from neutrons, not resistance from quarks, but resistance from spacetime itself. Imagine trying to compress a sponge. At first, it yields easily. Then more pressure is required. Eventually, you reach a point where further compression becomes increasingly difficult. Some physicists wonder whether spacetime behaves similarly. Perhaps there exists a fundamental limit beyond which geometry itself cannot be compressed, a minimum scale built into reality, a final layer beneath which no further structure exists. If so, the collapse of a neutron star might ultimately encounter a quantum foundation that prevents the formation of a true singularity. The result could be an object unlike anything currently known. Neither neutron star, neither black hole, something entirely new. These possibilities become even more fascinating when we consider the information paradox introduced in the previous chapter. Classical black holes appear to erase information, yet quantum mechanics strongly suggests that information cannot be destroyed. This tension has driven decades of research, and many proposed solutions involve radical revisions to our understanding of black holes. Some theories suggest that information is encoded on the event horizon itself. Others propose that information escapes through subtle quantum processes. Still others imply that the interior structure of black holes is vastly more complicated than classical relativity predicts. In each case, the black hole ceases to be a simple endpoint. Instead, it becomes an active participant in the deeper workings of reality, a bridge between known physics and unknown physics, a laboratory where the universe experiments with concepts we have not yet fully understood. There is a certain irony here. For generations, black holes were viewed as cosmic dead ends, places where matter vanished, places where questions stopped, places where nothing interesting could emerge. Now the opposite may be true. Black holes may be among the most informative objects in existence. Their very paradoxes could contain clues to the next revolution in science. The deeper we investigate them, the more they seem to point beyond themselves, towards something larger, towards something deeper, toward a framework that unifies the fundamental forces of nature. And perhaps that is why the collapse of a neutron star feels so compelling. It is not merely the death of an object. It is a journey through layers of reality. Each stage strips away familiar assumptions. Each stage reveals hidden structures beneath them. The neutron star already exists beyond ordinary matter. The black hole exists beyond ordinary gravity. What comes next may exist beyond our current understanding entirely. Some physicists have even entertained possibilities that sound almost unbelievable. Could collapse eventually connect to another region of spacetime? Could quantum effects create bridges between distant parts of the universe? Could the interior of a black hole contain structures radically different from anything visible from outside? Most of these ideas remain speculative. Many may ultimately prove incorrect. Yet speculation has an important role in science. It explores the landscape of possibility. It identifies paths that observations may later confirm or reject. And throughout history, today's speculation has often become tomorrow's accepted reality. No one once believed atoms existed. No one believed time could slow down. No one believed space could bend. Reality repeatedly surpassed imagination, which raises an intriguing question. Suppose the collapse of a neutron star continues far beyond everything we currently understand. Suppose spacetime itself begins undergoing quantum transformations. Suppose singularities disappear and new structures emerge. What would the object actually become? Would it still resemble a black hole from the outside? Would it possess an interior? Would it contain matter at all? Or would the distinction between matter and spacetime finally disappear completely? These questions take us to the very edge of modern physics, a region where theory becomes increasingly uncertain, a region where some researchers have proposed perhaps the most radical idea of all: the possibility that black holes are not merely objects within the universe, the possibility that they are connected to the creation of entirely new universes. There is a moment in the history of every great scientific idea when it begins to sound less like science and more like philosophy. The Earth moving around the sun once seemed absurd. The existence of invisible atoms seemed absurd. The idea that time could slow down seemed absurd. Even black holes themselves were once regarded as mathematical curiosities rather than physical objects. Again and again, reality has demonstrated that the universe is under no obligation to remain within the boundaries of human intuition. And so, when physicists began asking whether black holes might somehow be connected to the birth of entirely new universes, the idea initially sounded almost impossible. Yet the question emerged naturally from the equations, not because scientists wanted it to be true, but because certain paths within mathematics seemed to point in that direction. To understand why, we must return once again to the singularity. For decades, the singularity represented the ultimate dead end. Everything that crossed the event horizon appeared destined to fall toward an infinitely dense point where space-time itself ceased to function. But as we discussed earlier, many physicists doubt that true infinities exist in nature. If singularities are instead replaced by some deeper quantum structure, then a fascinating possibility appears. The story may not end at the center of the black hole. Something else may happen there. Imagine a collapsing neutron star continuing inward. The density increases. The curvature of space-time grows. Matter becomes compressed beyond anything we can currently describe. Yet instead of reaching infinite density, quantum effects eventually become dominant. At this stage, space-time itself may behave very differently from what classical relativity predicts. Instead of collapse continuing forever, the process could encounter a quantum limit, a kind of ultimate resistance hidden within reality itself. And then something remarkable might occur. The collapse could reverse, not outward into our universe, but inward into a new region of space-time, a region disconnected from the one in which the black hole formed, a region that expands rather than contracts, a region that behaves astonishingly like a young universe. This idea appears in several forms across modern theoretical physics. The details differ from one model to another, but the underlying concept remains similar. What appears from our perspective as a black hole may correspond, from another perspective, to the birth of a new expanding cosmos. In this picture, black holes become something far more than astronomical objects. They become cosmic seeds, gateways through which new universes emerge. The neutron star collapses, the black hole forms. The singularity is avoided, and somewhere beyond our observable reality, a new space-time begins to grow. Whether this is true remains unknown. There is currently no direct evidence supporting the existence of baby universes. Yet the idea is not pure fantasy. It arises from genuine attempts to understand what quantum gravity might allow. And what makes it so captivating is the way it transforms our view of cosmic endings. We often think of collapse as destruction. A star dies. A neutron star collapses. A black hole forms. The story appears to move toward greater simplicity and finality. But perhaps nature does not see collapse as an ending. Perhaps collapse is also a beginning. After all, this pattern appears throughout the universe. Stars die and create the heavy elements needed for planets. Exploding stars seed future generations of stars. Galaxies merge to create larger galaxies. Death and creation repeatedly become part of the same process. The boundary between endings and beginnings grows difficult to define. Perhaps black holes participate in this pattern as well. Perhaps what appears to us as an endpoint is, from another perspective, an origin. The idea becomes even more intriguing when we consider our own universe. Modern cosmology suggests that everything we observe emerged from an incredibly hot, dense early state, approximately 13.8 billion years ago. As we trace cosmic history backward, the universe becomes denser, hotter, more compressed. The similarities to gravitational collapse become difficult to ignore. In one case, matter collapses inward. In the other, the universe expands outward. Mathematically, there are surprising connections between these processes. Some researchers have wondered whether our own cosmos could have originated through a mechanism similar to black hole formation. Could our Big Bang have emerged from the interior of a black hole existing in another universe? Could our entire observable cosmos represent the continuation of a collapse that occurred somewhere else? Again, these ideas remain speculative, yet they reveal something profound about the questions black holes force us to ask. At a certain point, the study of extreme gravity begins merging with the study of cosmic origins. The smallest scales and the largest scales become intertwined. The fate of a collapsing neutron star becomes connected to the birth of universes, and perhaps this should not be surprising. Nature often reveals hidden unity beneath seemingly unrelated phenomena. Electricity and magnetism were once separate mysteries. Space and time were once separate concepts. Matter and energy were once distinct categories. Later discoveries revealed deeper connections. The universe repeatedly rewards those willing to look beneath appearances. Black holes may be another example. What appears to be an isolated object could actually participate in a much larger cosmic process. Yet even if baby universes never exist, the underlying lesson remains valuable. The collapse of a neutron star teaches us that reality contains layers far beyond ordinary experience. Every stage of the journey forces us to abandon familiar assumptions. Atoms disappear, neutrons disappear, perhaps singularities disappear, perhaps even space-time itself transforms. The deeper we travel, the more the universe begins to resemble something fluid and evolving rather than fixed and permanent. This realization carries a subtle philosophical implication. Human beings often seek ultimate foundations. We want final answers, the smallest particle, the deepest law, the final level of reality. Yet history consistently undermines that expectation. Every apparent foundation eventually reveals another layer beneath it. Every endpoint becomes a doorway. Every certainty becomes provisional. Black holes embody this lesson perfectly. They were once thought to be simple, gravitational prisons. Now they have become some of the richest sources of unanswered questions in all of science. Far from closing the book on understanding, they may be opening entirely new chapters. And this brings us back to the neutron star that began our journey. Imagine its final moments once more. A dead stellar core suspended against gravity, mass accumulating, pressure rising, collapse beginning, neutrons dissolving, exotic matter emerging, the event horizon forming, the black hole taking shape. At first glance, it seems like a story of destruction, but perhaps it is really a story of transformation, a story about hidden possibilities emerging under extreme conditions, a story about reality revealing deeper structures when pushed beyond ordinary limits. And perhaps the most remarkable thing is that we still do not know where the story ultimately leads. The collapse continues beyond observation, beyond measurement, beyond direct experience, into a region where theory becomes our only guide. There, at the edge of understanding, one final mystery waits. Because even if black holes represent the most extreme objects in the universe today, they are not eternal. Given enough time, even black holes themselves may eventually disappear. And if that is true, then the final fate of a collapsed neutron star may be stranger than anything we have discussed so far. There is something deeply unsettling about the idea of permanence. When we look at mountains, they seem permanent. When we look at oceans, they seem permanent. When we look at stars scattered across the night sky, they too appear permanent. Yet science has gradually revealed a different picture. Mountains erode, continents drift, stars exhaust their fuel, galaxies evolve. Nothing remains unchanged forever. The universe appears to be a place of ongoing transformation, a place where every structure, no matter how vast, eventually gives way to something else. For a long time, black holes seemed like the exception. Once formed, they appeared eternal, the ultimate gravitational traps, cosmic prisons from which nothing could escape. A neutron star might collapse into a black hole, but after that, the story seemed finished. The black hole would simply remain, silent, dark, permanent. Yet in the 1970s, an extraordinary realization emerged. A realization so surprising that even many physicists initially struggled to believe it. Black holes are not completely black, and they are not eternal. The discovery came from one of the most brilliant minds of the 20th century, Stephen Hawking. By combining ideas from quantum mechanics and general relativity, Hawking uncovered something astonishing. Black holes should slowly emit radiation. Tiny amounts of energy should leak away from the region surrounding the event horizon. Over immense spans of time, this process causes the black hole to lose mass, slowly, almost imperceptibly, but inevitably. The black hole begins to evaporate. At first glance, this sounds impossible. How can something escape from an object whose defining feature is that nothing can escape? The answer lies in the strange nature of quantum reality. According to quantum field theory, empty space is not truly empty. Even the vacuum contains activity. Tiny fluctuations constantly appear and disappear. Virtual particles emerge briefly before annihilating one another. The vacuum is not a silent void. It is a restless ocean of possibility. Near the event horizon of a black hole, these fluctuations can behave in unusual ways. A pair of particles may appear. Normally, they would vanish almost immediately. But if one falls into the black hole while the other escapes, the result is different. The escaping particle becomes real. Energy leaves the system, and the black hole loses a tiny amount of mass. This process is now known as Hawking radiation. The effect is extraordinarily weak for large black holes. A stellar mass black hole formed from a collapsed neutron star would emit only a minuscule amount of radiation, far less energy than it absorbs from the surrounding universe. At present, the process is essentially invisible. Yet, over sufficiently long timescales, the consequences become profound. The black hole slowly shrinks, its mass decreases, its event horizon contracts, and eventually, after an almost unimaginable duration, the black hole disappears entirely. To appreciate the scale involved, we must leave behind ordinary notions of time. Human civilization has existed for only a few thousand years. Recorded history occupies a tiny fraction of that. The dinosaurs disappeared 66 million years ago. The Earth itself is roughly 4.5 billion years old. The Sun will survive for another several billion years. These numbers already seem enormous, yet the lifetime of a typical stellar black hole dwarfs them all. A black hole formed today from a collapsing neutron star could survive for around 10 to the power of 67 years or longer. The number is so vast that it almost loses meaning. Trillions upon trillions upon trillions of ages of the universe would pass before the black hole finally evaporated. By then, nearly everything familiar would be gone. Stars would have ceased shining. Galaxies would have changed beyond recognition. The cosmos itself would be entering an era almost impossible to imagine. And still the black hole would remain, slowly fading, slowly shrinking, patiently approaching its final moment. There is something strangely poetic about this. The neutron star that once resisted gravity for millions of years eventually collapsed. The black hole that replaced it then survived for incomprehensibly longer. Yet even that was not forever. Gravity wins. Then time wins. Everything continues evolving. Everything continues changing. Even the darkest objects in existence cannot escape the passage of cosmic history. But Hawking radiation introduces a mystery far deeper than the death of black holes, because it forces us to confront a troubling question. What happens to the information? Recall the neutron star before collapse. Every particle possessed properties. Every interaction encoded information. Every arrangement of matter represented a particular state of reality. Then the neutron star became a black hole. From the outside, much of that information appeared hidden behind the event horizon. And now the black hole itself is evaporating. The Hawking radiation escaping from the horizon appears almost random, thermal, featureless. It seems to carry little information about what originally formed the black hole. This creates a profound problem. If the black hole eventually disappears completely, what happened to everything that fell inside? Where did the information go? Quantum mechanics insists that information cannot simply vanish. The fundamental equations preserve it. Yet Hawking's original calculations appeared to suggest otherwise. For decades, this contradiction became one of the most important puzzles in theoretical physics, the information paradox. Some researchers argued that information must somehow be encoded within the outgoing radiation. Others proposed that remnants survive after evaporation. Some suggested that information remains stored on the event horizon itself. Entire branches of modern theoretical physics have emerged from attempts to resolve this question. What makes the paradox so important is that it touches the foundations of reality. It is not merely a technical issue about black holes. It concerns the nature of causality, the nature of memory, the nature of physical law. If information can truly be destroyed, then our understanding of quantum mechanics requires revision. If information cannot be destroyed, then our understanding of black holes requires revision. Either way, something profound must change. And this is why black holes remain among the most valuable objects in science, not because we expect them to provide easy answers, but because they expose contradictions. They illuminate the places where our theories no longer fit together. The collapse of a neutron star ultimately leads us to these contradictions. The journey begins with stellar evolution. It proceeds through neutron matter, then quark matter, then black holes, then Hawking radiation, and finally arrives at questions about the deepest architecture of reality itself. Questions that remain unresolved, questions that may guide physics for generations to come. There is a certain beauty in that. The death of a star becomes a pathway toward understanding existence. An object only 20 kilometers across becomes connected to the largest mysteries in the universe. Gravity, quantum mechanics, information, time, and space-time all converge within the same story. And yet, despite everything we have explored, one final mystery remains. Perhaps the deepest mystery of all. Because even if black holes evaporate, even if information survives, even if quantum gravity ultimately resolves every paradox, there is still a larger question waiting behind them. A question not about what happens inside black holes, but about why reality allows such extraordinary objects to exist in the first place. After following a neutron star through its final journey, after descending through layers of matter stranger than anything found on Earth, after crossing the threshold of black holes and confronting the limits of modern physics, it is worth pausing for a moment and looking at the larger picture. Not the details, not the equations, not the particles, but the deeper pattern hidden beneath them all, because there is something remarkable about the story we have been exploring. At first, it appears to be a story about death. A massive star exhausts its fuel, its core collapses. A neutron star forms. Gravity eventually gains the upper hand. The neutron star collapses again. A black hole emerges. The object disappears behind an event horizon. Everything seems to move toward destruction, toward simplification, toward an ending. And yet, the closer we examine the process, the more complicated that interpretation becomes. The collapse of a neutron star is not merely destruction, it is revelation. Every stage strips away another layer of appearance and exposes something deeper beneath it. Atoms disappear and reveal nuclei. Nuclei disappear and reveal neutrons. Neutrons disappear and reveal quarks. Classical spacetime begins to fail and reveals the possibility of quantum geometry. Every collapse becomes an act of discovery. Gravity functions almost like a cosmic archaeologist, removing layer after layer of structure until only the deepest foundations remain. This is one reason extreme objects are so valuable to science. Ordinary environments hide many of nature's secrets. The world around us is stable, comfortable, predictable. Most matter exists under conditions that conceal its deeper possibilities. But neutron stars do not permit such concealment. They force matter into extraordinary states. They reveal behaviors that remain invisible everywhere else. And black holes push even further. They challenge our assumptions about space, time, information, causality, reality itself. The universe seems to reserve some of its most profound truths for its most extreme environments. There is something almost philosophical about that. Human beings often search for understanding by looking outward. We build larger telescopes, more powerful detectors, more detailed instruments, and these efforts have revealed astonishing things. Yet some truths become visible only when nature itself performs experiments beyond our technological reach. Neutron stars and black holes are among those experiments. The cosmos creates them naturally, then leaves them scattered throughout space like clues, waiting to be interpreted. In a sense, every black hole is a question mark written into the universe. Every neutron star is a puzzle. Every collapse is a challenge directed toward future generations of observers. Can you understand what happened here? Can you uncover the rules that govern this transformation? Can you see beyond the horizon of current knowledge? The remarkable thing is that these questions remain open. For all our scientific achievements, we still do not possess a complete description of reality. General relativity and quantum mechanics remain unmatched in their respective domains. Yet they refuse to merge cleanly. The deepest theory remains hidden. The final framework remains undiscovered. And perhaps that fact carries an important lesson. There is a tendency to imagine science as a process of accumulating answers, a gradual movement toward complete understanding. But history suggests something more subtle. Science often advances by discovering better questions. The discovery of atoms did not end inquiry. It created new questions. The discovery of relativity did not end inquiry. It created new questions. The discovery of black holes did not end inquiry. It created some of the deepest questions humanity has ever asked. Every answer expands the frontier. Every breakthrough reveals a larger unknown beyond it. The universe seems inexhaustible in this regard. No matter how far we travel, another horizon appears. And perhaps this should not discourage us. Perhaps it should inspire us, because the existence of mysteries means reality remains larger than our current understanding. There are still discoveries waiting, still insights hidden beyond the edge of knowledge, still chapters of the cosmic story left unwritten. Neutron stars embody this beautifully. When they were first proposed, many scientists doubted they could exist. The idea seemed absurd. Matter compressed to such extraordinary densities felt impossible. Yet observations eventually confirmed their existence. Then came new mysteries. What happens inside them? What is their maximum mass? Do quark stars exist? Can strange matter form? What occurs during final collapse? Each answer produced new questions, and those questions led naturally toward black holes. Then black holes generated even deeper puzzles, information paradoxes, quantum gravity, event horizons, holography, the possible birth of new universes. A single collapsing star became connected to nearly every major frontier of modern theoretical physics. This reveals something important about the structure of knowledge. The universe is not divided into isolated topics. Everything connects. Stellar evolution connects to nuclear physics. Nuclear physics connects to particle physics. Particle physics connects to quantum theory. Quantum theory connects to gravity. Gravity connects to cosmology. And cosmology ultimately loops back toward questions about origins, existence, and reality itself. The deeper we investigate any phenomenon, the more interconnected everything becomes. The boundaries between disciplines begin dissolving. The same may be true of reality itself. Perhaps the separations we perceive are temporary conveniences, useful categories rather than fundamental truths. Matter and energy were once considered distinct. Now we know they are different aspects of the same thing. Space and time were once separate. Now they form a unified spacetime. Particles and fields were once treated independently. Now they appear deeply intertwined. Again and again, deeper understanding reveals hidden unity. It is possible that our current distinctions between matter, spacetime, information, and gravity may eventually undergo similar transformations. Future physics may reveal a framework in which these concepts emerge from something even more fundamental, something we have not yet imagined. If so, then neutron stars and black holes may represent windows into that deeper level, places where familiar categories begin breaking down, places where the next conceptual revolution is already leaving traces. There is also a more personal lesson hidden within this story. The collapse of a neutron star reminds us that limits are often where the most interesting transformations occur. Stars become neutron stars because they reach their limits. Neutron stars become black holes because they reach their limits. Physics itself advances when existing theories reach their limits. Growth frequently occurs at boundaries, at thresholds, at moments when old structures can no longer remain unchanged. Nature seems to treat limits not as endings, but as opportunities for transformation. Perhaps that pattern extends far beyond astrophysics. The universe is filled with transitions, birth and death, creation and collapse, expansion and contraction, order and chaos. Yet these opposites often turn out to be interconnected parts of larger processes. The distinction between ending and beginning becomes increasingly difficult to define. A dead star creates the elements needed for future worlds. A collapsing neutron star may create a black hole. A black hole may reveal clues about quantum gravity. What appears final from one perspective becomes foundational from another. And so, after all this exploration, one realization remains. The ultimate significance of neutron stars may not lie in what they are. It may lie in what they teach us. They teach us that reality extends beyond intuition, that nature remains capable of surprising us, that certainty is temporary, and that the deepest mysteries often emerge precisely where understanding appears to end. As we prepare to conclude our journey, one final question remains. Not a question about neutron stars, not a question about black holes, but a question about ourselves. What does it mean that the universe contains objects so strange, so extreme, and so far removed from everyday experience? Why should a cosmos capable of producing conscious observers also produce neutron stars, event horizons, and the possibility of realities beyond black holes? As we reach the end of this journey, it is worth remembering where we began, with a single question. What happens when a neutron star finally collapses? At first, the question seemed straightforward. A massive star dies. Its core survives. Gravity continues its work. The neutron star eventually crosses a critical threshold. A black hole forms. Case closed. Yet the deeper we traveled, the more that simple answer dissolved. The neutron star became more than a dead stellar remnant. The black hole became more than a gravitational trap. The collapse became more than a physical process. What began as a question about an object gradually transformed into a question about reality itself. And perhaps that is the most remarkable thing about science. The greatest discoveries rarely answer only the questions we ask. Instead, they reveal questions we never knew existed. The collapse of a neutron star forces us to confront some of the deepest mysteries in existence. What is matter at its most fundamental level? What happens when space-time reaches its limits? Can information ever truly disappear? Does a singularity exist? Can black holes give rise to entirely new realities? Where does the chain of explanation finally end? Or does it ever end at all? These are not merely technical questions. They are questions about the structure of existence. Questions about what kind of universe we inhabit. Questions about whether reality possesses a final foundation or an endless depth. And what is striking is how often the universe responds with the same message. There is always another layer, Every time we believe we have reached the bottom, another level appears beneath it. For thousands of years, the stars seemed like the highest frontier. Then we learned that stars were only a small part of a larger cosmos. Atoms seemed fundamental. Then they were not. Particles seemed fundamental. Now even that assumption is uncertain. Space and time once appeared absolute. Then relativity changed everything. Each generation discovers that the universe is larger than the generation before imagined. Not merely larger in size, larger in possibility, larger in complexity, larger in mystery. The neutron star embodies that lesson perfectly. It is an object that should not seem possible. Matter compressed beyond ordinary imagination. Gravity approaching its limits. Physics operating under conditions almost completely detached from everyday experience. And yet neutron stars are real. They exist throughout the galaxy. Silent reminders that reality is stranger than intuition. Then beyond them come black holes. And beyond black holes come questions for which we do not yet possess answers. It is almost as though nature deliberately places its greatest mysteries just beyond the edge of current understanding. Not so far away that they are unreachable, but far enough that they continue drawing us forward. There is something profoundly human about this relationship with the unknown. Our species has always been attracted to horizons. Ancient explorers sailed beyond visible coastlines. Astronomers mapped the heavens. Physicists explored the atom. Each horizon revealed another. Each discovery expanded the frontier. Black holes represent one of the newest horizons in that long story, not because they are physically distant, but because they occupy the edge of comprehension itself. They mark a boundary where our current theories begin to fail, a boundary where future discoveries are waiting, and perhaps that is why they captivate us so deeply. When we look at a black hole, we are not merely looking at an astronomical object. We are looking at a question written into spacetime, a question that the universe itself appears to be asking. What lies beyond this point? What happens when our understanding reaches its limit? What comes after the last horizon? No one knows. And that uncertainty is not a weakness of science. It is one of its greatest strengths. Science does not claim certainty where certainty does not exist. It does not pretend the mystery has been solved. Instead, it acknowledges the unknown and continues exploring. The history of knowledge is not the history of final answers. It is the history of increasingly profound questions. The collapse of a neutron star reminds us of that, because the closer we move toward ultimate explanations, the more reality begins to resemble an endless landscape rather than a completed map. Each peak reveals another range beyond it. Each horizon reveals another horizon. The journey continues. Perhaps one day humanity will discover a successful theory of quantum gravity. Perhaps singularities will finally be understood. Perhaps black holes will reveal their deepest secrets. Perhaps we will learn whether exotic objects exist beyond them. Perhaps we will discover whether new universes can emerge from gravitational collapse. Or perhaps entirely unexpected answers await. History suggests that the universe rarely chooses the path we anticipate. Its greatest revelations often arrive from directions no one predicted. And that may be the most exciting possibility of all. The story is not finished. The neutron star has not given us its final lesson. The black hole has not revealed its final secret. The universe has not spoken its final word. Somewhere in the darkness between the stars, neutron stars continue spinning. Black holes continue growing. Gravity continues shaping spacetime. And reality continues unfolding according to laws we are still struggling to understand. The cosmos remains unfinished from our perspective, an open question, a living mystery, and perhaps that is exactly what makes it so beautiful. Tonight, as you imagine that distant neutron star approaching its final collapse, you can picture more than an object disappearing into darkness. You can picture a doorway, a threshold, a place where known physics fades into possibility, a place where matter becomes mystery, a place where even black holes may not represent the end of the story. Because if the history of science has taught us anything, it is this. Whenever we believe we have reached the final answer, the universe quietly reveals another question waiting beyond it. And somewhere beyond the collapse of a neutron star, beyond the event horizon, beyond the limits of our current theories, another question is waiting still. Perhaps one day it will be answered. For now, it remains part of the vast and beautiful unknown. Thank you for joining this journey through one of the deepest mysteries in modern physics. If you enjoyed this exploration, and if you would like more calm, thoughtful journeys into the hidden structure of reality, consider subscribing to Science Sleep Theory. And as the stars continue their silent evolution across billions of years, and black holes linger in the darkness beyond sight, perhaps leave a comment with one final thought. If a neutron star collapses beyond a black hole, what do you think waits on the other side? Until next time, sleep well, stay curious, and keep wondering about the mysteries hidden in the darkness between the stars.